Apparently, I seem to be coming through just fine. So let's go ahead and get started. You probably saw a little, this meeting is being recorded flash on the screen. So we are going to record this a little later. We're going to probably do some breakout rooms. And from what I understand, it doesn't record while we do that. So we're going to record about the first half hour or so. So if you do not want to be recorded, leave now or forever hold your peace, right? I'm Kelly Roos. I am your host tonight. I've been involved with this little organization called PICUP for quite some time. And I'd like to welcome you to this special edition of the PICUP Spring Webinar Series, Physics for Tomorrow, Enhancing the Curriculum for Things Contemporary, right? Our special guest presenter tonight is Crystal Bailey from the American Physical Society. I believe, Crystal, correct me if I'm wrong, your official title is the head of career programs, but Crystal guides many more projects beyond the implication of that particular title. Most relevant for tonight is her direction of the NSF-funded pipeline project. If you haven't heard of that, I'm sure she'd be happy a little later to pop up a website so you can go see that. It's a program focused on integrating workforce relevant skills into undergraduate physics physics education. I almost said physics correction. I don't know if that was a Freudian slip or not. Physics education. All right, so it's very relevant to what we're going to try to do tonight. Just a little bit of a background before I turn it over to Crystal. Even though computation shows up in the PICUP name, we've advocated an integrated curriculum for quite some time. And by this integrated curriculum, we mean, if you've been around us at all, you've probably heard us mention this three-legged stool of theory, experiment, and computation. And thanks to our good colleague Marie, also a fourth leg, communication. So when I got wind of the existence of this pipeline project, Crystal and I met about a year and a half ago, and we decided to form an exploratory group called Physics for Tomorrow. And you could think of this as our coming out party. This is our first real event, and we want to get some input, and we want to make this as engaged and as interactive as possible, right? So there's two important facts, and I'm going to let Crystal elaborate on these, but there's two important facts that we should think about, which suggest we should at least revisit the traditional undergraduate curriculum. One is less than half of physics undergrads go to grad school. And the second one, there's a less than 5%, I don't know the exact number, less than 5% probability that a BS in physics will become a tenured physics professor. So maybe we shouldn't continue to try to recreate ourselves, right? So as custodians, this ultimate experience in critical thinking and problem solving that we all know is this grand thing called the physics curriculum, should we be integrating into our courses activities that more directly align with marketable skills, even if these activities should greatly deviate from traditional topics and subject matter, right? So here's the plan. Crystal's gonna give us a brief presentation. After that, we're gonna do questions. I'm sure this will probably stir up some good questions for discussion. So I think we'll have time for some questions right after she's done presenting. I think we'll do that via the chat window, and I'll try to moderate this. And then somewhere in the neighborhood of the top of the hour, we'll break up into breakout rooms and try to have an integrated discussion with a smaller group. And then we'll come back and have a little report out. We'll end promptly, and I'm thinking Central Time, by the way, about 8:30 Central. There's no pressure to stick around. If you want to stick around, however, we'll open it up for maybe however long you want to go, half hour or so, maybe, for open discussion. All right, that's the plan. So may I introduce to you Crystal Bailey of APS. Take it away, Crystal.
Okay, great. Thank you, Kelly, very much for that great introduction of me and our effort, our Physics for Tomorrow effort. Can everyone hear me? We good? Okay. All right. Well, I'll go ahead and dive in. I will say, one thing I'd like to just mention is I will go through some statistics. I'll probably go through them a little bit quickly because people physicists, we are very numeric and we love to kind of latch on to statistics. Of course, I'm happy to sort of answer questions about it, but I definitely also want to kind of get to the punchline, which is a little bit more is richer than just what the statistics are telling us. So just wanted to let you know if I seem like I'm going through the stats pretty quick, that's the reason why. Okay, so just a little bit of context. Teaching the physics for tomorrow. So to kind of frame why, I don't know if y'all are familiar with Simon Sinek, but he gives a lot of talks about design and things like that. And he has this infamous video, start with why. A lot of times we tend to start with what and then talk about why. But talking about why, physics has maybe a little bit of a dodo problem, an endangered species problem, in that there are some things going on in our discipline. There are a lot of closures of physics departments. And I think that in particular, smaller sort of 4-year schools, bachelor serving institutions, we hear a lot lately with all kinds of changes going on that a lot of these departments are really kind of fighting to stay open, stay relevant, to get the resources that they need in order to continue doing the work that they do. We also know for a fact, have actually known for quite some time, that there is an abysmally low participation in physics of women and minoritized students. I think if you compare different STEM fields and what the representation is of women and also people of color, physics and engineering are both right there at the bottom, with even math doing somewhat better than we are. A thing that is kind of driving that, and in fact this is kind of verified by the most recent team up report that AIP put out, that a lot of the students that are coming into colleges, the demographics of students that are wanting to come to school to earn degrees, the demographics are changing, and also what motivates those students and also those who advise them are also changing. A lot of students who are coming in are maybe first generation college students. They really prioritize majors that will lead to well-paying, stable, and rewarding careers. That's not to say that students from these groups don't also see the beauty and wonder in discovering the universe, but they also very much think of these kinds of factors, like, does my degree actually lead to a good paying job, a stable job, and a job that will actually allow me to give back to the community and make an impact in the world. So these are considerations that are really, really important for today's students. And the third thing, students are not adequately prepared for diverse outcomes. So yes, a lot of physics graduates do find employment. There's a very, very low unemployment rate for physics graduates, but when you actually speak to the employers who hire physics graduates, they'll tell you that there is a lot that they do not know, that would have made them even more effective folks, things that they had to be trained for. And when you think about the fact that physics majors are often competing with engineering graduates for the same jobs, it does put our graduates at a disadvantage to not try to be more intentional about the skills that we give them, so that when they go into these private sector environments, that they're very well prepared. And of course, there's also the fact that, physics graduates have a great history of innovation. They're really good at thinking outside the box. They're generalists. Often physics students can talk across disciplinary lines. And so we're not capitalizing on the potential that physics graduates have to create really exciting and innovative solutions to problems that the world is facing. So these stats at the bottom, I'm actually going to go into a little bit more detail just really quickly. This is the stats heavy part. All these stats are from the AIP, Statistical Research Center. So the most recent report I had access to was 2015, 2016, but I've looked at these every time a new report has come out, and they haven't changed dramatically. The initial employment sectors of new physics bachelor graduates, 66% in the private sector. So that is by far the largest employment base of those physics bachelors who went straight into the workforce. Now, about a third went into graduate school in different fields, physics and astronomy, and then another, the half went into the workforce and the remainder went into other fields. But of those who went into the workforce, most of them were in the private sector. And this is what I was getting at before. When you look at the title, when you look at the field of those careers in the private sector, engineering and computer science are often kind of what those jobs are labeled as. That doesn't mean, that the students aren't still physicists. They still bring the expertise of being physics majors to the table. That's why they're recruited deliberately for those positions, but they are the same title, the same positions as many of these engineering computer science grads. Looking at masters, about 45% of master's degree recipients entered or remained in the workforce between 2016 and 2018. You'll notice a pattern. The largest employment base of all those master's degrees was also the private sector, and you actually have a pretty similar, not identical, but similar situation to the bachelor's in that of those who went into the private sector, you see that a lot of them were in these engineering and computer science fields. And between 2015 and 2016, 1,500 PhDs remained in the US workforce. That's the rate per year that was happening. So if you look exactly at just the initial employment of those physics PhDs, what sector were they in? Wow, it looks really great for academia. But the thing is, that also includes postdoc positions, temporary assistant lecturers, assistant professors, all of those kind of temporary positions that are actually becoming increasingly well represented. A lot of the tenure permanent positions in academia are being sort of replaced by these full-time temporary positions. And in my view, those aren't the real jobs that a lot of students are looking for that has security, well-paying, good benefits, and all those kinds of things. So when you actually just highlight those permanent jobs, that don't have a built-in expiration date, picture looks more like that. So clearly, industry has the largest number of those kinds of permanent jobs available as well. Also, about a quarter of these new faculty hires got their PhD outside of the United States. So I was just looking at the cohort that graduated in the United States. There's a bunch that come from outside the US. So all told, when you look at the whole picture, about 18% of physics bachelor's graduates will choose to finish a PhD in physics. And so if we think about somebody who gets a PhD in physics and then does 2 postdocs and assistant and then tenure professor, we think about the so-called traditional path, which it hasn't been the most common path for at least 30 years. But for some reason, we still call it that. About 5 out of 100 US-based physics bachelors will become traditional permanent physics faculty. And over half of them, closer to 70% of them, will work in a private sector job with either a physics bachelor's, master's, or PhD. So just some stats, just to kind of set the stage. But here's what we really want to get to today. When we talk, so we have a dodo problem. So how do we evolve as a discipline? And evolution for physics means broadening our vision of who does physics, what physics is, and why we do physics. What do I mean by who? As I already mentioned, the demographics of students who are going into college and wanting to major in the sciences is changing. Students' career goals and aspirations are important. They're important to their mental health and well-being. They're important to the success of programs, to making sure that students who are coming into your program are being heard in terms of what they actually want and not being othered, for example, because they don't want an academic career. And there, like I said, there are stakeholders who also influence decisions of students who also need to be taken into account when we think about how we talk to students about what we offer in physics. What content is taught to physicists, right? Of course, it's very important to understand physics and these really great truths about the universe and all this scientific knowledge. There's also tremendously valuable analytical skills, technical skills, computation, lab skills. But to prepare them for these careers, we also need to be teaching them things like communication. Communication is one of the most important skills that any employer looks for in a physics graduate that they're hiring. And being able to innovate, being able to think outside the box and be creative. And as part of physics, we really need to be making that connection all the time between how the physics that students are learning can actually enable them to make a positive impact in the world. And that relates to, why do we do physics? We need to emphasize the potential for physics graduates to contribute to human challenges. And at the same time, okay, we can continue to promote a sense of wonder at discovering new knowledge, but we also need to examine the privilege that is inherent in centering careers that are solely based on sort of knowledge for the sake of itself, and marginalizing the desire to also want to make good money, have a stable job, and make an impact. So this shift from a technocentric to human-centric design will allow for a larger and more diverse community of students to recognize the value of studying physics. So physics for tomorrow, just a little bit, quick bit of background. So as Kelly already mentioned, the APS pipeline project started, kind of launched in 2016. I have to say that I feel like pipeline suffered from a little bit of a branding issue, because we are focused around the concept of physics, innovation, and entrepreneurship education. And I think when a lot of people heard the word entrepreneurship, they kind of thought, startup, Silicon Valley, like it just didn't seem like what they wanted to get involved in. It also seemed really far away and like not within their realm of comfort. When in fact, what we have always been advocating for is a physics curriculum that integrates the learning areas of Phys 21: scientific and technical skills, communication skills, workplace relevant skills, and physics specific knowledge. That's actually what pipeline has always been focused on, but that wasn't clearly communicated. Meanwhile, both Alpha and PICUP, we've been having conversations with folks, Kelly and others, recognizing that a growing cohort of educators are starting to realize that, like, wow, we really need to rethink our approach here to what kinds of skills we're trying to impart to our students in the physics curriculum. So as we kind of got together and put our heads together, we kind of defined a rubric for physics for tomorrow, as we're defining it, which are activities that ensure that students experience integrated technical skills and advanced problem solving, encouragement of teamwork and open-ended thinking, which is so important when these students go to work in industry. They're solving new problems and discovering new things, right? That's true even for research. Communication that's relevant in diverse contexts and with diverse stakeholders. Physics that's contextualized in real world situations and have applications to real world problems. So design-based projects, for example, that consider technical and economic aspects of a product. Demonstration of critical professional and life skills like independent learning, working collaboratively, and an emphasis on the potential for social impact. So you may be thinking, wow, that's a lot. That's a lot that I don't know how to teach, which is completely fair. And, I think the reason we're here today is that, we don't have the answers either, but there is a nascent community of folks who are interested in exploring this. And some approaches do already exist. I know you're familiar with PICUP and Alpha and, building in those advanced lab skills and computational skills. And if you go to epic.aps.org, the pipeline final report from our effort has finally been published. And up there, you'll see Pi Library, which will show you all of the curricular materials that were developed as part of pipeline. My favorite one of all the ones is a project in introductory physics based on the Hyperloop, Elon Musk's Hyperloop. And it uses basic kinematics to build this hypothetical scenario of this train that's, going at really high speed, and then it stops at certain places, and the students figure out how much time it adds and how much energy loss there is, and then the students start to think about, okay, well, how would you design this so that it's not stopping? And then they get in this whole design innovation space. So check it out. There's some things out there. Also, what we've developed are just suggestions. There are so many other approaches. And I think the thing also is that you want to start small, start smart, start small, um, and work on what you can. And this is the really important takeaway I want you all to hear. Because I think the most intimidating aspect of this, like when we've presented these ideas to physics faculty, they're like, great, now I'm supposed to teach all this extra stuff on top of the physics that I'm already teaching. But what we've tried to do with Pipeline is really integrate these approaches into the physics curriculum that you're already teaching. So it's not building onto, but building into ways to just kind of modify your module. And there's some really cool approaches that are on that website. But like this is my analogy. So we've got this cat that is physics, right? We're not suggesting that we build on, feathers and a beak and make it into something else by adding on. What we're actually suggesting is that we evolve. Here's our new animal. So it's a combination. It's got the feathers, it's got the beak, it's got all those little things, but it's still this integrated being. And yeah, I think that's all I had to say. So thanks.
All right, thank you, Crystal. So if I would have been on top of it, we could have had some kind of award or something for identifying which movie this is from. I actually learned something new in planning for this meeting tonight. I hadn't seen the movie that it came from. I don't know, maybe we can, well, I don't know. I'll think about some kind of anyway. Oh yeah, Crystal already said. Anyway, thanks, Crystal. So I think what we'll do is let's field a few questions. Hopefully this induced some interest and some questions from you. So I'm going to go back and I'm going to look at the chat window. So I'll ask these. Let's do this for about 7 or 8 minutes. Don't be offended if there's lots of questions I don't get to them now. We're going to come back in about a half hour or so after our small group meeting part and have an open discussion. But let's go through some now. Crystal, this was back when you'd first started. Someone asked, are physics departments closing faster than departments in other fields? Do you have any idea about that?
Well, my impression is yes.
Mhm.
And I think what is happening, what my understanding is what is tending to happen is that physics departments are being subsumed into other departments. And so, instead of having a standalone physics department, it's physics and engineering, or, it kind of gets lumped in with and sometimes it does happen to multiple departments, but it is happening to physics quite a lot. And yeah, there are other departments where, yeah, physics programs are definitely closing because they're not graduating anywhere near the number of majors that, say, engineering or some of the other STEM areas are graduating.
Mhm. Okay, I think this is more of a comment. We hear about graduates in all fields. Always companies feel students are not prepared. I think that's probably true in general, right?
Mm-hmm.
Usually you get feedback along those lines.
Right.
Let's see. Thank you. The AIP Statistical Research Center is great. I've made use of the career data for many years. Another comment. This is from Chitra, I believe. I would like some practical examples of changes that departments have started making. Do you know any sort of, what would we call it, Crystal? Any case studies of places that have embraced Phys 21 or
I can definitely give a couple of examples of places that have done, I think, an exceptional job. Mount Holyoke blew my mind. And again, it's been a while since I visited them, and certainly you'd want to. I don't have the stats on like how many majors they are graduate. Like I don't have those cold hard facts, but I can tell you that what I saw when I went to visit their department really blew my mind. because
Hmm.
they embraced a lot of what we were talking about. They have this lab space that is actually in the art building, but it is a co-used space between physics majors, computer science majors. I don't know that they have an engineering school, but I can't remember. But they're like definitely computer science, physics, other STEM, biology, other STEM areas, and it's sort of it's a makerspace, but it's very well designed. There's the requisite 3D printer. They have the Arduino programming station. They've got a sewing area. They've got a laser cutter. They've got a mold, like a thing that they make plastic kind of molds and stuff. And what was so striking about it is that lab is also co-taught by individuals who are faculty in different STEM departments. And what was so amazing about it, certainly the physics folks and the people in STEM were learning all kinds of great technical stuff about how to design and build things. But when I was there, one of the people programming in Arduino was a Russian studies major.
Hmm.
And this person was talking about how cool it was that they were learning coding, and I met another person who is in lighting design in the theater program, and she was like, yeah, I want to go into lighting. I'm going to have to be like controlling these boards and all these different complicated light shows and programming this stuff in. So just to see them really engaged with this kind of technology and learning. They're also like really smart things, like, at every station they had a QR code where you could scan it and it would show you a video of how to run the thing. What I loved about that was that it really engaged everyone, and it what is it, encourage cross disciplinary collaboration, which is actually a really important aspect of the skills that our students need to be learning, because they are going to be working on interdisciplinary teams. So learning how to actually communicate well to different people, work with them, recognize the intelligence and the strengths that other folks actually bring to the table. That's a thing that physics majors have also been kind of identified as not being great at by employers who hire from across STEM.
Mhm. Um, let's see, Aaron's question was pretty much along the same lines. Steve Gottlieb asked, is the pipeline program holding workshops for faculty? Before Crystal answers about the pipeline, this is something we intend after we break up into the small groups pretty soon here. We're going to come back for a little report out and then a wrap up. And part of the wrap up tonight, we're going to put to you all, what would you like to see? We have kicked around the idea of actually holding a workshop along these lines. I don't know if, Crystal, you can address the specific pipeline question, but as a PFT organization, this burgeoning thing we're trying to create here, we're thinking about doing this and would like to get some feedback if that's would be something of interest.
Yeah, Kelly, absolutely. Well, I can say that so pipeline's winding down as a distinct thing, and so you could kind of say that all of our individual efforts are also evolving into a new animal, which is maybe PFT, right? And so we definitely did have lots of workshops. We really tried to kind of engage folks with limited success. Like I said, I feel like we had a branding problem. Like people just weren't. I think they were scared off by the entrepreneurship in our title. So we had workshops. We didn't have a lot of folks participating. Um, and there was one other like thing I wanted to respond to, which is a Laszlo asks that the AIP showed the number of physics faculty increasing. Yes, I don't have this slide here, but it's one of my favorite ones to show, because if you yes, it has been increasing. It's gone up by like 50 in the past 6 or 7 years. No, about 10 years. It's gone up by like 50. The whole thing oscillates between like 400 down to like 325 and then back up to 375. The number of PhDs that are being generated, it's a big swoop up, and the scale is 1800. It's like an order of magnitude scale difference. Um, and in fact, if you take the ratio in 2010 of the number of new PhDs to the number of faculty hired, it's something like 16%. And okay, so you delay it by 6 years because people graduate and they spend 6 years doing postdocs. If you take the 2010 graduates and then the increased number in 2016, it's like 23%. It's tiny. So, yeah. Sorry, Kelly, I didn't mean to interrupt your.
No, that's quite all right. So I think the bottom line is we're considering doing something more along these lines. Maybe more of these type of meetings, or maybe an extended symposium of sorts, or maybe even a workshop. So we'd like to get feedback of who might be interested, and you can contact me, Crystal, and anybody that we can point out some more of our PFT members here before we leave tonight.
There'll be an AAPT session on Physics
yes.
for tomorrow too.
Yeah, thank you, Ben. That was perfect interjection. Yes, there is an AAPT, an invited session, and I don't think the schedule's out yet, so that's something to, we'll certainly advertise that.
Yeah. And before we go to the breakouts, I just see that multiple people were asking the question about how would the PFT physics graduate be distinguished from an engineer? Great question. And again, in another version of this talk, the way that they're distinguished is physics graduates already, by virtue of being physics majors, have a certain. So first of all, yes, great scientific knowledge, great scientific and technical skills. We know that that's strong. That's an aspect of what we're teaching our students that's very good and we need to preserve. And that's also a thing that employers are looking for. The way that physics graduates are special, and the way that we should continue to strive to be special, is that physics graduates are more comfortable getting solutions from first principles. Or framed another way, physics graduates have the confidence that they can teach themselves what they need to know in order to move to the next step. They're not liable to come up to the edge of their expertise or their training or whatever kind of system or model that they have been kind of taught, and find that a situation doesn't fit that model and just say, oh, well, it's not what I do. I don't know what to do. Physics graduates are they believe that they have the ability to learn whatever they need to learn, or they have the appropriately general foundation to actually try things and come up with new solutions. And that is absolutely a special thing that should be celebrated about physics graduates, and that should be held onto. And I would actually say that what we're proposing for the PFT curriculum, open-ended thinking, it actually builds on that strength rather than replaces it.
Mm-hmm. So I think what we should do, because we very much like to engage everybody who shows up to these and have an interactive session. So I'm going to suggest that we go to our breakout rooms. I believe there's going to be 4, and we'll be somewhat randomly